Welcome back and good afternoon, everyone. Today I'm going to show you a quick video on how to do the springs lab, mass on a spring. And so again, we can simply copy paste the link, but I will just go here. I will go to Sims, Simulations, Physics, and let's see. I will uncheck all these boxes and I will just choose this one because it opens on HTML5, so it should be here. So let's look it up. It's about springs. So not the basics, this one, masses and springs. So click on it. It should open on the browser. I'm using Chrome. And then choose the lab tab, this one, lab. Okay, so I have it and I'm going to, I can attach masses here. I can change the mass value. So let me just choose 50 grams at first. And let me put this one. This one will measure the displacement. So meaning, let me grab a meter stick first and align it here. Notice this is in centimeters. So this is 10 centimeters here. And so let me attach so let's see here. In the first part of the lab, we want to measure the force constant of this spring. So let me just hit here so the table won't hang at the end of the page. So we want to collect data for mass versus extension, the amount by which it extends. I did the first data point here at 50 grams. So when there is no mass attached, the spring is not extended at all. So this is 0. So when it's 50 grams, which is 0.0, you divide by 1,000, 0.05 kilograms, and mg is the force, so that's 0.49 newtons, right? You multiply it by 9.8 mg, it's in newtons, those are the units. By how much will it extend? I said 8.5 centimeters. Let's just double check. So let's go to 50 grams, and it starts to oscillate. I can increase the damping just to stop it quick, and then make the damping 0 again. Let me move the meter stick here so it aligns with the ruler. So this is 9 centimeters, 8 centimeters. So it looks like between 8 and 9. So if you think it's 8, fine, you can put 8 centimeters. I put 8.5 because it seems like 8.5. So there's, we can disagree on about half a centimeter probably. So that's fine. My eyes are just as good as yours. Maybe yours are better. It's just very hard to see, especially on a laptop on the screen. Maybe if you have a big screen, you can see better. But anyways, 8.5. And you will do this for 100, 150 until you have data collected. So you will plot the extension versus the force, and you will plot the force on the y-axis, the extension on the x-axis, and using this F equal to kx, you can extract the force constant of this spring. Now, okay, fine. And now we're going to let our mass oscillate. So we're going to let our mass oscillate. So let me show you how that goes. So let's say if I pull my mass down, it will start oscillating. Okay, it will start oscillating, and it has a certain period and so on. So let me just damp it so it stops. And I'm going to get a clock here or a timer. I'm going to click pause here. So make sure you click this. It just makes life easier. And I will click start for the clock. So the clock will not start, even though I put start, until I start here. And then I will pause it from here. So here's what I mean. So let me pull down on the mass. I'll pull it to about 20. It doesn't matter where you pull it, actually. I'll pull it to about 20. You see, it still hasn't started oscillating because I paused the whole program. That's why I paused it from here. And now I'm going to let it start and oscillate. It would be inaccurate to measure the period for just one cycle because it's hard to tell. But I want you to measure the period for 10 cycles. And here I said the period for 10 cycles is 5.9 seconds. I did the first data point for you. Let's do it and see if I can get 5.96 seconds again. So let's start. So one cycle means it starts here, it will go up and come down. That's one cycle. So let's do it. I'm sorry. Let's start over. because there is lots of damping. I don't want the damping. So let me start here. Pull it down to 20. No damping now. So now it will oscillate freely. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I stopped. 5.98 seconds. I put 5.96. So there will be some disagreement in there, right? A few milliseconds, a few hundredths of a second for each of us. So you can get 5.96, I get 5.98. Somebody might even not quick enough and click, maybe it's 6 seconds, or maybe clicks too soon, it's 5.92. That's okay, as long as we're about the same number. And we're going to go down this path and fill out the table. So when 50 grams are attached, this is the period. This is the time for 10 periods. So divide by 10 to get the time for just one period. And we're going to get the period squared. So take this number and square it, so you get this. And now next thing you will hang 100 grams, then 150. So here is how it looks like. So if I hang 100 grams, I just go to the slider here and increase it to about 100. That's about 100. And then I will do the same thing. And then I will just, I need to make this 0 again. Click start. So it hasn't started yet until I put start, and it will start going up and down. Okay. And you will do 10 periods there. And then you're asked to plot the period versus the hanged mass, and or the period squared versus the hanged mass, and then from that, using this relationship, you will be able to calculate K, and you will get K from here, right? That's K. And I ask you to calculate the percent difference between the K you got from the first part here, this part, and then the K that you got here using the percent difference formula. So that's the end of this.